One retired cruise liner gave back 55,000 tons of steel and 2,000 tons of copper, enough raw material for countless other industrial products from a single hull. The tricky part is getting it out without a fatal fire or polluting the coastline. Watch the full journey from the beaching yard to a stadium roof, then decide where ship recycling should happen next. Every ship you see cruising the ocean has an expiration date. A modern container carrier can stretch over 400 meters long, taller than a 100-story building if stood on end, and packed with over 30,000 tons of steel. Somewhere out there, a scrapyard already has its name written down. But retiring one of these giants is nothing like scrapping a car. A commercial ship this size holds hundreds of kilometers of wiring, thousands of meters of piping, and dozens of separate engineering systems. And every last one has to be mapped before anyone lights a torch. Nobody just walks in swinging. Surveyors walk the whole ship before anything else happens. Fuel tanks, sludge pockets, asbestos insulation, PCB coatings, pressure vessels, batteries. Anything that can burn, poison, or explode has to be logged on a hazard map. Every corner gets a red circle or a green one. Then comes the moment the ship stops being a ship. In beaching yards, the vessel runs itself onto a sand slope at full throttle so the tide can leave it grounded. In dry docks, it gets floated over blocks and drained. In alongside yards, it sits at a quay while cranes pull it apart piece by piece. 3 approaches, 1 destination. The bigger yards look like small industrial cities. A single top-tier recycling facility can move the same volume of steel each year as a mid-sized steel mill produces. Rows of hulls sit in different stages, some fresh off the last voyage, some already skeletonized. In beaching yards along the coast of India and Bangladesh, the scale gets ridiculous. Dozens of hulls sit nose first on the sand at low tide, each waiting its turn. Workers walk out to them on foot. Cranes stand ready on the shoreline. But before any torch touches steel, the ship has to be made safe to touch at all. Here is the part most people never guess. Shipbreaking does not start with the sparks you see flying. Before any torch fires, gas teams sweep every enclosed space for fuel vapor that could still ignite. A tank that reads empty on paper can still hold enough vapor to level a city block. Only after the safe reading do the torches come out. Workers in coveralls climb onto the ship with cutting gear, slice the funnel free from its mounts, and the crane lifts it clean off the top of the vessel. Then come the pipe runs, the engine room fittings, the smaller kit, all cut and lifted piece by piece. A hydraulic grapple below sorts what falls to the ground. Ships built decades ago can still hold tons of oily muck stuck to the bottom of ballast and fuel tanks, so cleaning always comes first. Then comes the removal of anything that would poison the steel later. A grapple pulls apart interior structures, tearing away insulation, wall panels, and lighter fittings. Asbestos gets bagged separately. Old wiring bundles come out for copper. Some ships from decades ago contain enough banned materials to make a safety inspector nervous. Now the interior gets stripped. Cabin fittings, doors, wall panels, wiring bundles, and thousands of smaller items get pulled out and sorted into separate piles on the yard floor. Wood goes one way, plastic goes another. Cable bundles get bagged for copper recovery. Ferrous scrap heads to the heavy pile. A ship this size can produce more scrap categories than most Home Depot's stock aisles. And this is where the payoff of clean stripping shows. Roughly 85 to 98% of a properly recycled ship's mass can be reused, but only if it comes out sorted, not mixed. A clean ship pays, a dirty one costs. Not every ship makes it to the yard in one piece. When a vessel runs aground and breaks up at sea, salvage crews pull the wreck out chunk by chunk with floating cranes, then barge it to a recycler. But the real prize is still bolted to the engine room floor. Now the recovery crews turn to the most valuable part of the ship. The engine room is where the real money sits. A large marine diesel engine can stand as tall as a 4 or 5-story building and put out power equivalent to tens of thousands of car engines running at once. Around it, live generators, turbochargers, pumps, heat exchangers, and control systems worth 6 figures on the resale market alone. Crews spend weeks disconnecting piping, draining lubricants, unbolting mounts, and lifting each component out through openings cut in the deck above. This is where a ship stops being scrap and starts paying for its own recycling. Modern facilities do this work with tower cranes and floating platforms. A big yard can process up to 100,000 light displacement tons of ship every year, running dozens of hulls in parallel. Cutting blocks come off the ship and travel across a concrete, impermeable floor to be broken down further. The old picture of shipbreaking on a raw beach is not the whole industry anymore. Then the recovery team goes after the shaft and propeller. A propeller shaft on a large cargo ship can weigh dozens of tons and stretch tens of meters through the stern. Pullers grip the shaft, apply hydraulic force, and slide the whole assembly out of its bearing tube in one controlled motion. You do not just pop that out with a screwdriver. Behind every wall on that ship is a maze of pipe. If you laid out all the piping in one large cargo vessel end to end, you would cover tens of kilometers, easily. Fuel lines, ballast lines, cooling water, lubricating oil, steam, compressed air, sewage, firefighting. Each one carries a different fluid at a different pressure, and each pipe joins the next through flanges, valves, elbows, and reducers. Crews trace each system before touching anything, drain it clean, disconnect the flanges with hand wrenches, and pull the pipe out in manageable sections. Bronze valves get sorted separately from steel pipe because they sell for a very different price. Stainless goes in its own labeled pile. Copper cooling lines come out clean and shiny and head straight to the non-ferrous buyer. The ship you thought was one big steel box turns out to be a plumbing museum inside. Sorting on site is where the yard makes its margin. Mixed scrap sells for one price. Cleanly separated non-ferrous metal like copper, brass, bronze, and aluminum can sell for multiples of that. The difference between a yard that separates and one that does not is the difference between breaking even and turning a profit. Non-ferrous metals get their own dedicated stream. Shredders break down, mixed scrap, magnets pull out steel, and eddy current separators split the aluminum from the copper. A ship's electrical harness alone can yield tons of copper wire, and copper, on any given week, is worth its weight in patience. In some parts of the world, this recovery still runs on human labor at the scale of a small town. Crews walk the beaches, cutting, sorting, hauling by hand. Bangladesh alone produces roughly 80% of its domestic steel supply from shipbreaking. When the wrecked cruise liner Costa Concordia was finally dismantled, the yard recovered around 55,000 tons of steel and 2,000 tons of copper from one hull. One ship, 1 year of yard work, and a small nation's worth of raw metal ready to go back into the industry. Now the biggest phase begins. The superstructure, bridge, accommodation block, funnel, gets cut off first because it sits on top and has nothing pressing down on it. Even one cabin block can weigh as much as several suburban homes stacked together. Cutting the top of a hull is like unbuilding a small skyscraper. Workers climb up onto the deck, drag oxygen and fuel gas hoses behind them, and light cutting torches that burn hot enough to slice thick steel plate in one pass. The bridge tower comes down floor by floor, section by section. Each cut piece has to be planned carefully, so it falls in a controlled direction that clears the ground crew below. Get the cut sequence wrong, and a section starts to lean before the last piece of steel lets go. Get it right, and a many-ton block drops exactly where the ground crew wants it. On a busy yard, cutting torches burn 12 hours a day, and the top deck of the ship shrinks visibly every week. Sparks rain down, chain slings tighten. The ship gets shorter one level at a time. Below the superstructure sits the main deck and the bulkheads that divide the interior. A large cargo ship holds thousands of tons of steel just in these two systems alone. The deck is not a plain plate. It is stiffened underneath by hundreds of longitudinal beams, transverse frames, and hatch combings that have to be cut separately from the deck plate above them. Bulkheads are even worse. Every watertight wall inside the ship was built to seal off floodwater in an emergency, which means it was welded solid on all four edges to prevent leaks. Crews open each wall with a torch, drop the freed piece onto the deck below, and hook it onto a crane for hauling to the yard floor. The deeper you cut into the ship, the more you realize how much steel it actually takes to hold water out of a moving hull. And then the heavy machinery gets its turn. An iron claw the size of a small house mounted on a hydraulic arm bites through hull steel like it was cardboard. The claw grabs, twists, tears, and drops the piece into a growing pile of scrap. You do not need finesse when you have that much hydraulic pressure, but you do need excellent aim. Side shell and double bottom hold most of the tonnage. These plates kept the ocean out for decades. Excavators with hydraulic shears bite through them, section by section, exposing the deep girders below. But cut pieces still are not scrap yet. They have a long road ahead before they melt. Now the ship stops looking like a ship and starts looking like a job site. Blocks that came off the hull get lowered onto the yard floor for a second round of cutting. One block resting on the ground can weigh more than the total payload of a full convoy of long-haul trucks. Ground crews walk around each piece with cutting torches, dropping it into smaller sections that can actually be lifted, sorted, and hauled. Excavators equipped with hydraulic shears bite through frames and stiffeners. Others with grapples pick up loose plate and stack it by type. Trucks arrive to haul finished piles to the dockside, where a barge waits to carry it to the next stage. A dry dock that held one ship a month ago now holds thousands of tons of sorted metal ready to travel. Modern yards handle this second cut with serious hardware. A crawler crane rated at 200 tons picks up cut blocks and moves them to a dedicated secondary cutting zone, away from the hull. Skilled cutters then work through each block, breaking it into pieces sized to match what buyers actually order. A smaller excavator arranges the finished sections in a stacking area, ready for sale and delivery. The whole yard flows like a slow-motion butcher shop, but for steel. Hydraulic shears do the heavy tearing. Mounted on the end of an excavator arm, a top-shelf industrial shear can generate cutting forces of several thousand tons, enough to snap through structural I-beams and plate steel like it was cardboard. The operator swings the arm into position, closes the jaws, and a section pops free with a bang that echoes across the yard. You do not so much cut with these things as convince the steel to give up. Robust jaws, thick armor plates, and a wear-resistant tip mean one shear can chew through hulls for years before it needs rebuilding. For loose ferrous pieces, an electromagnet does the sorting itself. A crane lowers a heavy-duty magnet over the pile, powers it on, and lifts steel while leaving non-magnetic metals like aluminum and brass behind. Physics gets the first pass. Once sorted, scrap streams start leaving the yard. Heavy melting scrap goes one direction, Clean plate goes another. Machinery blocks, non-ferrous piles, and copper bundles all get their own labels. Trace-level copper contamination in the wrong pile can throw off an entire steel heat downstream. Then the scrap starts moving from land to sea. Trucks arrive one after another at the John Lorry Quay, back into their assigned spots along the mooring, and tip their beds onto heavy steel pads laid down to protect the concrete below. A material handler fitted with a specialized grapple scoops up the pile and drops each load with precision into the ship's open cargo hold. A wheel loader keeps sweeping the spillover back into reach. Truck, loader, grapple, ship. A four-way handoff that runs until the hold reads full and the hatches come down. Large bulk carriers do the international leg. A shore crane lowers a bin of processed scrap over the open hold and dumps it in, load after load, until the ship reads full draft. Steel is one of the most traded raw materials on Earth. American yards run the same play with their own equipment. At a facility in Brownsville, cranes lift stripped hull sections onto the ground, torch crews slice them into standard sizes, and rolling stock hauls the finished product out to steel mills across the country. Every yard has the same problem to solve: how to turn a ship into truckable, meltable, saleable steel. Loading a scrap ship is not as simple as pouring gravel. Weight has to be spread evenly across the hold, or the vessel lists. Cranes swing bin after bin into precise positions. But even a full hold of ship-cut steel is still not ready to melt. The mill has its own opinion about what it wants delivered. Steel mills care about two things: chemistry and shape. A modern electric arc furnace melts hundreds of tons of scrap per heat, but only if the scrap fits neatly into the charge bucket and does not trap huge air pockets. Cars, refrigerators, tanks, appliance frames, and ship steel all end up at the mill. But each has to be sized right before it goes in. A mistake at the scrapyard becomes an expensive delay at a multi-billion-dollar mill later. Chunks too big get in the way. Pieces too hollow waste furnace space and slow the melt. Densifying scrap saves fuel and time. A denser charge means fewer buckets, faster melt, and lower energy per ton. Mills prefer bales, briquettes, or shreds because they load predictably and pack tight. Loose sheet metal wastes half the furnace volume before it even starts to melt. A 2,000-ton press with side compression squeezes bulky ship plate from the sides first, then chops it into blocks up to 25% more efficiently than a plain shear. The output looks like giant steel bricks stacked on a pallet. Heavy beams get their own treatment. A hydraulic shear on an excavator bites through structural I-beams and rails, snapping them into pieces short enough for a furnace charge. Then comes the check. Nobody skips. A handheld gamma and neutron scanner sweeps the pile before shipment, hunting for stray radioactive sources that might have hidden inside old medical equipment or industrial gauges. One hot piece in a full container can shut down a whole mill for days. Mills blend scrap like a recipe. A single flat roll steel plant can produce over 3.2 million tons of hot metal per year using recycled ferrous scrap as its main input. The charge bucket for each heat mixes heavy melting steel, shredded scrap, structural cut, and specialty grades in exact proportions to hit target chemistry. Operators check the mix, adjust ratios, and log every source lot for traceability. Modern steelmaking is basically industrial cooking at a scale where every burner runs at 3,000 degrees. Get the recipe right and the melt behaves. Get it wrong and the whole heat has to be scrapped. Now comes the payoff every recycling video builds toward. A charge bucket the size of a small building, loaded with hundreds of tons of prepared scrap, swings over an electric arc furnace on an overhead crane. The roof lifts aside. the operator releases the bucket. In seconds, an entire ship's worth of former steel plate crashes into a vessel that will melt it back into liquid metal within an hour. What was cruising the Atlantic 6 months ago is about to be sunlight, bright orange liquid. 3 enormous graphite electrodes descend from above, holding a fixed distance from the scrap pile, and an electric arc strikes between them and the metal. The whole furnace begins to hum with a low roar you can feel through the floor. Sparks shoot upward. The scrap starts sagging, then flowing, then puddling into a molten pool at the bottom. Slag rises as impurities separate. Oxygen lances inject through side ports to speed the reaction. Additives drop in from overhead chutes. The most recycled material on Earth is going through its next lap right in front of you. A modern electric arc furnace can melt up to 60 tons of scrap per basket load. Sorted scrap enters through the roof, the electrodes come down, and the arc between them heats to around 3,500 degrees Celsius. The melt reaches roughly 2,010 degrees Celsius before it flows out through a tap hole in the furnace floor into a receiving ladle, from cold scrap to liquid steel in about an hour, and that steel is roughly 100% recycled input. Charging looks like controlled violence caught on camera. The bucket bottom opens. Hundreds of tons of scrap crashes into the furnace shell, and steam bursts upward as any moisture on the metal flashes off in an instant. The roof swings back into place seconds later. Nobody stands close to that opening. Graphite electrodes do the heavy lifting. Each one is a machined column of ultra-pure carbon, made from petroleum coke and coal pitch through crushing, screening, calcining, kneading, extrusion, impregnation, roasting, and graphitization, a manufacturing chain measured in weeks. When power flows through them, an electric arc bridges the gap to the scrap and heats it to well above the surface temperature of most lava flows on Earth. These electrodes wear down every heat, and mills consume them by the truckload. A large steel plant can burn through multiple electrode columns per shift, each one machined to millimeter precision before it ever gets bolted into the furnace. The arc itself is what you never forget. 2 glowing streams of plasma dance between the electrodes and the melt, throwing sparks in every direction. Robotic arms manipulate additives from safe distance. The whole furnace throws off more raw heat than most people ever see in their lives. Every heat produces a mountain of slag. Oxygen, carbon, and lime added during the melt combine with impurities and float to the surface. The slag gets poured off into a slag pot, hauled by rail to a cooling yard, and eventually broken up with a wrecking ball. Steel making is basically 2 products, one you keep and one you throw away. After the primary melt, the steel gets fine-tuned. In a ladle furnace or an argon-oxygen decarburization vessel, operators inject gases, add trace, alloying elements like manganese and vanadium, and adjust chemistry until the grade matches the buyer's exact specification. Milligrams of a rare element decide whether the steel goes into rebar or a jet engine. From the ladle furnace, the liquid steel heads to continuous casting. Molten metal pours into a water-cooled mold, solidifies into a slab or billet, and slides out the bottom as a continuous ribbon of glowing red steel. A single modern casting line runs almost non-stop for days at a time. The output gets cut to length by an automated shear and stacked, ready for reheating and rolling. Now the shaping begins. Slabs and billets get reheated to rolling temperature, then squeezed between huge rollers that stretch them into thinner, longer shapes. A modern bar mill can produce hot-rolled coils, rebar, structural beams, wire rod, and precision bars all from the same input, just by changing rollers and pass schedules. A single rolled bar can stretch tens of meters before it gets cut down to commercial length. Precision sizing mills push tolerances down to fractions of a millimeter across the full length. High alloy grades come out the same shape as commodity rebar. The difference is what got mixed into the ladle furnace 2 stages back. Every batch gets tested before it ships. A robotic sampling arm picks bars off the cooling bed, cuts sample sections, measures dimensions, and weighs them for compliance. No steel leaves the mill without certified data attached. Buyers demand it, regulators require it, and insurance companies would refuse coverage without it. And this is where a ship becomes a bridge: fabricated steel box girders. Some of them made from recycled scrap that used to sail. Get trucked to a construction site on oversized trailers, launched over the water on rollers, and lowered onto piers with a launching nose taking the leading load. The completed structure carries traffic across rivers, seaways, and canyons for the next century. Somewhere in that steel is a fragment of a hull that crossed oceans decades ago. Rebar takes the same path in a different direction. Bundles of hot-rolled bar get shipped to construction sites, unrolled onto foundation slabs, and tied into the reinforcement grid that will sit inside concrete for the next century. The world produces close to 2 billion tons of steel every year, and steel remains the most recycled material on Earth. That is the payoff hiding behind every wrecking ball on every beached hull. A ship leaves the ocean, but its steel does not stop there. After dozens of steps: hazard mapping, cleaning, engine recovery, hull cutting, secondary shearing, sorting, testing, melting, casting, and rolling. What was once a hull crossing the Pacific becomes rebar in a hospital foundation or a beam holding up a stadium roof. The industry moves millions of tons of ship steel back into the global supply chain every year, and most people never notice. One of the biggest questions facing the ship recycling industry today is where recycling should take place. Should beaching yards in South Asia continue to dominate because of their lower costs? Or will stricter environmental and safety standards shift more recycling to dry docks in Europe, Turkey, and the Americas even at higher prices? Where do you land? Cheap and fast, or clean and slow? Tell us in the comments. If you got something useful from this walkthrough, tap subscribe and stay around for the next industrial deep dive. See you then. Take care.